In today's video, we are going to go over 5 different examples for the buoyant force in Archimedes' principle. Now, before we started with example number 1 says that we have this copper cube, which is 15 centimeters on each side, and we are going to take that copper cube and we are going to hang it from a spring scale, and we are going to put that copper cube in water like that, and we want to know when it's placed in the water, how much will the cube weigh? Now you can see I put weigh here in quotation marks because really when we weigh something, we often weigh it in air. That's what we think of as the weight. So this is going to be the apparent weight when that copper cube is in water. And now I told you that the density here of copper is 8,940 kilograms per cubic meter. So what we need to do is we need to figure out what the buoyant force is going to be, because the weight is pulling down. You can see that Fg, that's the weight of the object, that copper cube, and we have the buoyant force because it's in air, and that pushes up in the opposite direction. So that means if we hang it from a spring scale, the force on the spring scale, Fs, is going to be the weight minus the buoyant force. The weight pulls down and the buoyant force pushes up in the opposite direction. We can get the weight from Newton's second law, Fg equals mg, and we can get the buoyant force from this equation, which is that the density of the fluid, which is water in this case, is times the acceleration due to gravity times the volume of the object, or the volume of the water displaced, because they're the same, will give us the buoyant force. Now, the weight of the object, we need to get the mass. Now, I gave you the density and the volume, so you can get the mass from the density equation, which says that the density of copper is equal to the mass divided by the volume. We can rearrange that. We get the mass is equal to the density times the volume. If we plug the values in, we get that the mass is 8,940 kilograms per meter times, and we got to convert this into meters because this is centimeters, that's 0.15 meters. We cube that, and we get that the mass of that cube is going to be 30.2 kilograms. And now to get the weight is 30.2 times 9.81 from this equation right here, and that gives us that that cube weighs 296 newtons. So that is the weight. That's this value we need. Now we need the buoyant force. We can calculate the buoyant force from our buoyant force equation, which says that the density of the fluid times g times the volume is equal to the buoyant force, which this is the density of water, 1,000 kilograms per meter cubed. This is acceleration due to gravity, g, and this is the volume, once again, in meters. We got to cube it, and we get that the buoyant force is 33. So now we have the weight, we have the buoyant force, and the weight on the spring, the force on the spring scale is going to be the weight of the object, which pulls down, the buoyant force, which pulls or pushes up, and we get that that cube in water, the apparent weight, is 263 newtons. That is the end of example number 1, and now we can go on to example number 2, and example number 2 has to do with the buoyant force on a body. Now, we don't often think about the buoyant force in air, but we are in air, which is a fluid, and it does exert a buoyant force. It's not very high, as you'll see, because density of air is not very high. But we can figure out the buoyant force on a person who has a mass of 80 kilograms. Here's the density of the human body, which I just looked this up. I found a few different answers, but I got this values. And this is the density of air. And we can get the buoyant force on that person is that the density of air, because you're in air, times g times the volume. Now, once again, I didn't give you the volume. I gave you the mass this time and the density. So you can get the volume of a person from the density equation. The density of a person equal to the mass divided by the volume. The volume would be the mass divided by the density, and then that's 80 divided by 985 kilograms per meter cubed. You can see the kilograms cancel. You're left with 0.081 meters cubed. We can plug that into this equation, which is the density, the acceleration, and the volume, and you get that the buoyant force, your weight really decreases by 1 Newton when you're an 80 kilogram person approximately. Now, is that a lot? I mean, it's not a lot, but let's just see what that would be maybe in pounds. Okay, this is the buoyant force in newtons, and we can get the mass of that amount of weight in gravity, due to gravity, by taking Newton's second law, and we can take the mass is equal to the force, This force is due to gravity, therefore the acceleration is 9.81, and we get the mass is 0.105 kilograms, which is like 105 grams. How many pounds is that? Well, we can use this conversion factor because 1 kilogram is about 2.2 pounds, and we can see when you're in air, you weigh a little less. You weigh 0.23 pounds less. Now, it's not very much, but if the air was to go away, then you would weigh more, and that wouldn't be good. But if the air was to go away, then you would also be dead, so it wouldn't really matter. Okay, so there you go. That's example number 2. Now, example number 3 is we have this object, and when we measure it in air, when we weigh it, it weighs 12.5 newtons. Then we're going to place it in water, and its weight, its apparent weight, is 8 newtons. We want to know what is the volume of the object. Okay, everything has a weight on Earth. When we put it into water, it still has that weight, but we say it doesn't weigh the same because there's the buoyant force which pushes it up in the opposite direction. Okay? Now, the buoyant force is the force in air minus the force in water, and therefore the buoyant force is 4.5 newtons. We can just subtract those two. We don't need to use the other buoyant force equation. We want to know the volume. So here's the buoyant force equation, and there's the volume that we're going to solve for the volume. And when we solve for the volume, we get the volume as the buoyant force divided by the density of the liquid that it's in, the fluid that it's in, which is water. So that says the density of water times G. And therefore, we get that 4.5 newtons divided by 1,000 times 9.81. So the volume of that object is 4.6 times 10 to the minus 4 meters cubed. That kind of corresponds to that buoyant force like that, when we have those two weights in air and in water. Okay, that is example number 3. And now we can go into example number 4, which is a floating object. So this object is not submerged in water. It's floating, and we want to know, it's a piece of bamboo. We want to know what percentage of it is actually submerged in water. Okay, now the density of bamboo is 620. The density of water is 1,000. Now, you might know this intuitively, or you might see that maybe it makes sense that the answer is probably going to be 620 and 1,000. That's right, it's going to be 62%. Right? If you had something that has a density of half of water, then half of it will be in the water, half of it will be above the water. But we can actually use the buoyant force to come up with the answer to that and see where we get that 62%. Because we know that the bamboo has a force of gravity acting on it, and if that object is floating, then we know the buoyant force is equal. Those two forces are equal to each other, the force of gravity and the buoyant force. And the force of gravity is the mass of the bamboo times G, which is equal to the buoyant force, which is the density of water because it's in water, times G times the volume of the water that is displaced. Okay, when something is floating, we use the volume as the volume of the water that's displaced. It's always the volume, but in this case, it's not completely submerged. Okay, so now we can put in here here you can see here's the mass of the bamboo. Okay, we don't know the mass. Okay, but here you can see we can substitute in the density of the bamboo from the density equation, that the mass is the density times the volume. And you can see that we have G on both sides. So we can we can cancel G. That means we're left with the equation like this: the density of bamboo, volume of bamboo, is going to be equal to the density of water times the volume that is submerged, which is the same thing of those two volumes are going to be the same. And we can, not the same, but we can take the ratio of the two. The ratio of the volume of that is submerged, displaced there, divided by the volume of the bamboo is equal to the density of the bamboo divided by the density of the water. And therefore, we can take that ratio and we can divide the 620 by the 1,000, and you get 62%, or 0.62 or 62%. So that means the bamboo 62% of it would be underwater. Okay, now we have the last problem, and the last problem is the hot air balloon problem. And the hot air balloon problem looks like this. We have a hot air balloon, okay, I put here weather balloon, and it wants to lift a payload of 75 kilograms, okay? And the balloon, we're going to take into account the fact that it has a helium balloon, and the balloon actually has some mass. So the mass of the balloon is 1.25 kilograms. This is the density of air. This is the density of helium. And we know that the buoyant force has to lift those things up. So it has to be more than the weight of the helium. Now, I didn't put He here. This is not hydrogen. This is helium, H for helium. Then this is the mass of the payload, or the weight of the payload. And this is the weight of the actual balloon. Now, we know the buoyant force is the density of the air times the volume times G. Okay? We have a G in all of these terms. We can cancel that G out. And now we're left with this equation, which is the density of air times the volume is equal to, density of the helium times its volume, and the mass of the payload and the mass of the balloon. Now, I'm going to do two things, because we want to solve for the volume. We have two volumes here. They're the same volume. So I am going to subtract this term from both sides to get it to the other side, and I'm going to factor the volume out. And therefore, I get that the volume times the density of air minus the density of helium, because I subtracted this from both sides, so this makes this a negative term, is going to be equal to the mass of the package times the mass of the balloon. Not times, but plus the mass of the balloon. And then I'm going to solve for the volume, which means I'm going to divide both sides by this term, the density terms here. And I get that the volume of the balloon is equal to the mass of the package plus the mass of the balloon, which were both given, divided by the density of the air minus the density of the helium. This is helium again. All right, and those are given too. So we know if we plug those values in that we end up with just about 69 meters cubed. So in order at the surface of the Earth for a balloon to lift up itself and the package that and the helium that's in the balloon, because you got to take that into account. Here we did. You're going to need a balloon that has a volume of about 69 cubic meters. Okay, so there you go.
Hey there everyone, welcome back. This will be an example using Archimedes' principle to find what percentage of an iceberg's total volume is actually out of the water or above the water's surface. All right, so as you may or may not know, icebergs float in water, but more specifically, there's much more of an iceberg below the water surface than you see above the surface, okay? If you've seen the movie Titanic, you'll know. So let's draw a typical iceberg. So it might look like this, and then come down, and then maybe go over here and look like all this right there, okay? So that's my iceberg. The density of ice, as you see in the problem here, is about 917 kilograms per cubic meter. All right, so, density ice, right? The density of water, or rather seawater, slightly more dense than fresh water because seawater has such a high salt content, is about 1,029 kilograms per cubic meter. So let's do a simple, quick free body diagram analysis, right? Meaning, what forces are at play? Well, on this iceberg, you have its weight downwards, right? I'm going to say that's mg. And pushing up, right, preventing that iceberg from sinking into the ocean is the buoyant force, which I'll call FB. And that's it. All of the tiny hydrostatic forces on the surface that act every different way, this way, that way, this way, all that are perpendicular to the surface, right? They all act such that their horizontal components cancel out, regardless of what shape the iceberg is, right? So real quick, I'm going to draw a hypothetical hydrostatic force. Well, let's do it in black there. Okay, so in black, if I draw it like this, right, it has two components, the vertical and horizontal. So it has this component and it has that component, right? Well, on the other side of its center of mass, there's some combination of horizontal components here and there, here and there, here and there, wherever, that cancel out this component over there. Okay? And so the shape of this iceberg does not have to be symmetrical for those horizontal forces to cancel out. The only forces that don't cancel out are the vertical components, right? At every point along the surface, right? Even up here where the pressures are down, right? It doesn't matter. All vertical forces combine together to give, in effect, this singular buoyant force upwards that acts from the iceberg's center of mass. Okay? So, all that being said, we have two forces. The buoyant force equals the weight of the iceberg. And remember, we can write the buoyant force as rho GV, where rho is the density of the fluid that iceberg is displacing, right? Pushing out of the way. Rho, G, and V is whatever volume right here of fluid is being displaced. Right there. Okay? It's just the fluid displaced, not the entire volume. That comes into play when we determine the weight. Okay, so I guess we can say volume of water, if you will, right? Now, over here with mg, right, that's the mass of the ice, the total mass. And so for this, we need to rewrite mass in terms of density and volume, right? Remembering that mass equals rho times v. So the mass of the ice equals, or it can be written as the density of ice times the total volume of the ice, right? This now is all that plus the bit that's above the surface, right? It's the entire thing times g. Okay? So, as you can see, gravity cancels out. And now, what are we trying to find? The fraction of an iceberg's total volume that rests above the surface, right? So, in other words, we're finding a ratio. So, I'm going to find the ratio of, let's see, I want the volume of water displaced to the volume of the ice, the total volume of the iceberg. And so that's equal to the density of ice over the density of water, right? And so we know the values for both of those densities. So ice is 917 and seawater is about 1029, okay? And so this should give us, in my notes I have, it's roughly 92% or so, right? So in other words, the volume of the water is about 0.92 volume of ice, right? So that's the volume that's underneath the water. So the answer to this problem is only 8%, right? So only, we'll say, let's do it this way. So only 8% of the ice water, or of the iceberg, is above the surface. But we simply used Archimedes' principle, where the buoyant force is equal to the density of the fluid displaced times g times the volume of the fluid displaced. All right, there you go. Thanks for watching.
To review, hydraulic jacks, based on Pascal's principle, conform to this equation. The force on one piston divided by the area of that piston is equal to the force on the other piston divided by the area of that piston, which allows you to multiply a force based on the difference in areas between these two pistons. So here's our problem. A hydraulic lift's pistons have areas as given. What minimum force is needed for us to elevate a 1,420 kilogram car with the aid of the hydraulic lift? So let's start with this equation that applies for hydraulic lifts. Let's put in the numbers that we know. The area of one of the pistons is 0.0254 square meters. The other area is 1.33 square meters. And we need to put this force number 2 up here. That force is not 1420, but is rather 1420 times g, because this 1420 is simply the mass of the car, it's not the weight, and we need the weight of the car. So, if we cross multiply, solve that for F1, that tells us that we need to apply a force of 266 newtons to the smaller piston in order to lift that car, which weighs something around 14,000 newtons, which is a pretty good deal. Now the trade-off is that we have to move that force through a much bigger distance than the car is going to move through. Now for this problem, let's find the pressure on each piston. Well, pressure is force divided by area. So for the small piston, the force is 266 divided by the area. That gives us roughly 10,500 pascals, but I've just changed it into kilopascals. And the pressure on the larger piston is equal to the force divided by the area. And sure enough, they have the same pressure, which is exactly what we should expect.
Now let's start this video with a problem. A downward force of 100 newtons is applied to the small piston with a diameter of 50 centimeters in the hydraulic lift system shown below. What is the upward force exerted by the large piston with a diameter of 2 meters? So if we push down the small piston with a force, let's call it F1, the large piston is going to be pushed up with a force of F2. Now, according to Pascal's law, the pressure applied to an enclosed fluid is transmitted undiminished to every portion of that fluid. So what does it mean with regard to the hydraulic lift system? This means that the pressure exerted on a small piston is equal to the pressure exerted by the large piston. So we can say that P1 is therefore equal to P2. And pressure is defined as force divided by area. So since we're looking for F2, let's solve for it. Let's multiply both sides by A2. So here's the equation that you need. The output force, or the upward force exerted by the large piston, is going to be F1 multiplied by the ratio of the areas of the large piston with respect to the small piston. So if you exert a downward force on a small piston, you're going to get a larger upward force on the large piston. So the piston with the larger area is going to be associated with the greater force. And that's what you want to take from this hydraulic lift system. It's a force multiplying device. You can apply a small force on a small piston and get a larger force on the large piston. So let's go ahead and answer part A. Now the area is pi r squared because the pistons are circular in nature. Now we're given the diameter. The radius is half of the diameter. So if you have a circle, here's the diameter, and this is the radius. So F2 is going to be F1, which is 100 newtons, times A2, which is pi r squared. And the diameter of the large piston is 2 meters, which means the radius is 1 meter. Now the radius of the small piston is 25 centimeters since the diameter is 50. It's half of that. But we need to convert 25 centimeters into meters. So if we divide that by 100, that's going to be 0.25 meters. Now we could cancel pi. So 1 squared divided by 0.25 squared is 16. and 16 times 100 is 1600. So F2, the output force, is 1600 newtons. So that's the answer to part A. So let's move on to part B. What is the mechanical advantage of this hydraulic lift system? Mechanical advantage is the ratio between the output force and the input force. So the output force, the force exerted by the machine, is F2, which is 1600 newtons. The input force is the force that we applied to the machine, that's 100 newtons. So the mechanical advantage of this particular hydraulic lift system is 16. So if we were to apply an input force of 1000, this particular machine would multiply that input force by 16. So we would get an output force of 16,000. And so that's what the mechanical advantage of a machine tells you. It tells you what factor the machine will multiply your input force. So if we apply a force of 10 newtons, the machine is going to multiply that by 16 and exert an output force of 160 newtons. Now let's move on to part C. If the input force of 100 newtons pushes the small piston down by 2 meters, how high will the large piston rise? So we're going to push this down by a distance of 2 meters. How high will this piston rise? Let's call it D2. Now there's two ways to get this answer. The first way is to realize that the volume of the fluid inside the hydraulic lift system is the same. So typically there's some type of fluid inside this hydraulic lift system. And the change in volume in the small piston has to equal the change in volume of the large piston, because the volume of the fluid can't change. So therefore we need to say that V1 is equal to V2. The volume is the product of the area and the height. So V1 is A1 times H1, but we use D to represent the height. So you can say D is vertical displacement. So A1 times D1. And V2 is going to be A2 times D2. So A1, that's pi R1 squared, since we still have a circular cylinder. And A2 is going to be pi times R2 squared. So we don't need pi. We could cancel that in this problem. So R1, that's the radius of the small piston, is 25 centimeters, which is 0.25 meters. And then D1, we're pushing down the small piston by 2 meters. So D1 is 2. R2, that's half of 2, so that's 1. And so our goal is to calculate D2. So it's going to be 0.25 squared times 2. So D2 is 0.125 meters. So what does this mean? It means that there's no such thing as a free lunch. The machine didn't multiply our force by a factor of 16 from nothing. There was a cost, there was a price to pay for. Notice that the small force is associated with a longer distance, and the large force is associated with a smaller distance. So in order to multiply the force by a factor of 16, we had to pay the price by exerting the small force for a longer distance. And so the machine exerted a large force for a shorter distance. And so that's why the force was multiplied. The work has to be the same. The work done by the small force has to equal the work done by the large force, because energy has to be conserved. And so we could get this answer as well by using the conservation of energy principle. So the input work has to equal the output work. So the work that we apply has to equal the work that the machine will do if there's no friction. So this is the ideal situation. If this machine is 100% efficient, the energy that we apply to the machine has to equal the energy that the machine puts out as well. So the work done by the input force is just force times displacement, F1 times D1. The work done by the output force is going to be the same, F2 times D2. So we applied a small force of 100 newtons for a distance of 2 meters. And so the large force of 1600 newtons will be applied for a shorter distance of 0.125. So it's going to be 100 times 2 divided by 1600. And thus that will give you the same answer of 0.125 meters. So before we start this problem, you may want to pause the video to see if you could do it yourself. So we have a 1500 kilogram car, and it's placed on a large piston which has a radius of 4 meters. What is the minimum upward force that the large piston must exert to lift the car? Now gravity exerts a downward weight force on the car, which is mg. And the piston exerts an upward force, F2, on the car. So the minimum upward force that the piston has to exert in order to lift the car at constant speed is mg. If F2 exceeds mg, then the car is accelerating upward. But to lift the car at constant speed, those two forces have to be equal. So the net force is 0. So we can say that F2, the minimum upward force, has to be at least mg. So that's going to be 1500 kilograms times a gravitational acceleration of 9.8. So in this example, F2 is 14,700 newtons. So that's the answer to part A. Now let's move on to part B. If the mechanical advantage of the hydraulic lift system is 20, what is the minimum downward force that should be applied to lift the car? So we know that a small force is associated with the small piston, and a large force is associated with the large piston. So if the mechanical advantage is 20, that means that the small force has to be 20 times less than a large force. So it's going to be 14,700 divided by 20. So therefore F1 is 735 newtons. For those of you who want to use an equation to get the answer, here's what you need to do. The mechanical advantage is the ratio between the output force and the input force. So we're looking for F1. So first let's multiply both sides by F1. So F1 times mechanical advantage is equal to F2. So now we need to divide both sides by the mechanical advantage. So what we have left over is that F1 is going to be F2 divided by the mechanical advantage, which is what we did. And that's 14,700 divided by 20, and that gave us an input force of 735 newtons. Now let's move on to part C. What is the radius of the small piston? So how can we get the answer to that question? Well, according to Pascal's law, we know that the pressure exerted on these two pistons have to be the same. So that means that F1 over A1 has to equal F2 over A2. Now I'm going to rearrange the equations. So first let's cross multiply. So first we have F1 times A2, and that's equal to F2 times A1. Now I'm going to divide both sides by F1 and simultaneously by A1. So on the right side, A1 will cancel. And on the left side, F1 will cancel. So what this tells us is that the ratio of the forces, F2 over F1, is equal to the ratio of the areas, A2 over A1. And we know that mechanical advantage is basically equal to the output force over the input force. The output force being F2 and the input force being F1. So we could say that the mechanical advantage is basically the ratio between the areas of the large piston and the small piston. And in this example, the area is pi r squared. So A2 is going to be pi r2 squared, and A1 is pi r1 squared. So we could cancel pi in this problem. The mechanical advantage is 20. R2, that's the radius of the large piston, that's 4 meters. So that's going to be 4 squared. And we're looking for R1. So let's cross multiply. So 1 times 4 squared is 16, and that's going to equal 20 times R1 squared. So we need to divide both sides by 20. So 16 divided by 20, as a decimal, that's 0.8. So 0.8 is equal to R1 squared. So now, we need to take the square root of both sides. So R1 is 0.894 meters. As you could see, it's much less than 4 meters. So that's how you could find the radius of the small cylinder, or the small piston, if you know the radius of the large piston, and if you know the mechanical advantage. Now let's move on to part D. What is the pressure exerted by the large piston? So pressure is force divided by area. So the force exerted by the large piston, we know it's 14,700 newtons. And the area is pi r squared. And the radius of the large piston is 4 meters. So it's 14,700 divided by pi times 4 squared, or 16. So the pressure is 292.4 pascals. Keep in mind, 1 pascal is 1 newton per square meter. So that's the pressure in the fluid. And that pressure is exerted throughout the fluid. So the pressure on the small piston is the same as the pressure on the large piston. Keep that in mind. And that's based on Pascal's principle. Part E. How far should the small piston descend? So looking for D1 if we want to lift the car by 2 meters. So D2 is 2 meters. The easiest way to get the answer is to use conservation of energy. So the work done by the small piston is equal to the work done by the large piston. Or rather, the work done on the small piston is equal to the work done by the large piston. So F1 D1 is equal to F2 D2. So F1, we said, was 735 newtons. And D1, we're going to push down the small piston by some unknown amount. We need to calculate D1. And F2, that's the large force, that's 14,700. And we know that D2 is 2 meters. That's how high the car is being lifted up. Now keep this in mind. The large force is always associated with the shorter distance. The small force has to be exerted over a longer distance. So D1 should be much larger than 2 meters. In fact, since the mechanical advantage is 20, we know that the distance that we have to push the small cylinder down has to be 20 times the distance that the car is going to lift up. So the mechanical advantage is the ratio between D1 and D2. So D1 is going to be 20 times 2, so it's going to be 40 meters. So you can also use this equation to get the answer. Or you could say 14,700 times 2 divided by 735, and that will give you the same answer, 40 meters. So there's multiple ways in which you can get the right answer. So now let's review some formulas that you want to keep in mind when dealing with the hydraulic lift system. The first thing is the mechanical advantage is the ratio between the output force and the input force. And it's also the ratio between the area of the large piston and the small piston. And it's the ratio of the distance that you have to push down the small piston by the large piston. So if you increase the area of the piston, the output force will increase. But the distance that the large piston has to move will decrease. So make sure you understand that relationship. And also, if you need to find the output force, it's equal to the input force multiplied by the ratio of the areas. And if the cylinder is circular, the area is pi r squared. And keep in mind that the diameter is twice the value of the radius. This is not the distance that you push down the piston by. So just make sure you understand that. And then the input work, F1D1, has to equal the output work, F2D2. And the volume has to be constant. So V1 equals V2, and the pressure is constant. P1 is equal to P2. And for volume, you can say that A1 times D1 is equal to A2 times D2. So there's a lot of formulas that you could use for the hydraulic lift system. And so if you want to write them down, here it is. Thanks for watching.